In this video I will study the close range sideband noise of this selective amplifier, which I also use as an oscillator. It has been running now for 17 hours on my 2-channel signal analyzer, 2 receivers with correlation spectra of the phase noise. Look at the previous video for details about this. I will save this spectrum so I can evaluate the sideband noise levels. I can see already that at 50 Hz it's about -155 and 100 Hz here at about -165 dBc per Hertz. Here is the frequency response of that oscillator when running it as an amplifier. You can see it's very close to 50 ohms on 10 megahertz. And the gain is 3.2 decibels. I can look at the bandwidth. Here I get the Q as 107,000. And here is the schematic diagram of the input part. And to start with, I'm interested in this section, that is the filter. I will put a resistor parallel to the crystals to degrade the Q and to load it to get half the signal amplitude, because that way I will see the impedance at this point. Now I placed a 3.3 kilo ohm resistor in parallel with the crystals. That has reduced the gain from +3 to -3 dB, actually +3.2 to -2.7. So that's a 6 decibels loss, and the associated loss of Q is a factor of 2. It's now 54,000 as compared to 107,000 before. I have removed this capacitor and connected the filter like this. I have not changed the tuning here that gets the impedance, but I have on the output a voltage divider with capacitors and a trimmer, and I have set this trimmer to a minimum, very close to minimum, to get a very weak coupling to the output, to this resistor and to the 50 ohm load. The loss is now 44 decibels and the Q is 90,000. This means that there is some negative impedance on the gates of the FETs because I have not tuned precisely enough. I think that doesn't matter. What I will do now is to increase the coupling capacitor until I see some loss of the Q here. Now the loss is 20 dB and the Q is just degraded a little. Now I can measure the noise through this filter when using the Wenzel oscillator as a signal source. The filter attenuates by 20 decibels now. To compensate for that, I have increased the gain of the UADC4 and I have removed 2 decibels of attenuation that I was using before when measuring the Wenzel oscillator directly. Still, the level is 2 decibels lower than before, as you can see here, and the noise floor is much higher, particularly around DC. I have changed the gain setting from 3 to 13 decibels. So signal to noise ratio of the direct signals, the average power spectra here, has degraded significantly. This measurement has been running for 16 hours. I estimate the noise from the imaginary part, and it's down here, but at about 20 Hertz it starts to come too close, and at 10 Hertz it's about the same as the signal. And at wider separations the signal is the same as the imaginary part. So this is not very useful, but I can estimate the noise of the desired signal at, let's say, 30 Hertz and 40 Hertz with a reasonable accuracy. So this is what I can get out from this measurement. I have looked at flicker noise in crystal filters before. This is from some old video in this Nerds series with 20 crystals feeding by 0 dB, and then with a reduced signal level it behaves the other way as I would expect. Anyway, I have studied both with direct measurements similar to what I'm doing now, using another Wenzel oscillator, but also with interferometry, and get similar results. So these curves, they have the appropriate slope for flicker noise, and they are at about minus 144 at 10 Hertz. So those lines approximately fall where I have placed this pen. This diagram shows my oscillator, this amplifier I'm just now measuring on when running as an oscillator. It is this line, which goes very good at larger separations. This is 180 Hertz. This curve is the Wenzel oscillator I'm using now, and the red is from a paper where they published a very good oscillator last year. And you can see the performance at a wide separation. That paper is not so good, the Wenzel is good, but my oscillator is much better. But at close range it's the other way around. That paper is very good, it has a smaller slope, so at 1 Hertz it will probably be much better than the Wenzel, and my oscillator is really much more noisy at the close range. Now what comes from the crystal, this pencil, that is the total noise. I didn't measure phase noise and amplitude noise separately at that time, and it does depend on the power level. The measured value I have now are marked by these nuts. So this is the measurement that I have, and here I have compensated for the frequency response which I get from here, and the difference from here to here represents the flicker noise of the filter, and it's too small. I don't have the accuracy required to know anything about this at this moment. I have modified the 2-channel receiver. There were 2 6 decibel attenuators to set a suitable signal level for testing the Wenzel oscillator and not saturating the Schottky mixers. They were the limiting factors for the amplitude here. So I replaced these attenuators with low noise amplifiers and reversed the order between the low-pass filter and the amplifier. This has increased the level by something like 16 decibels. So I have reduced the gain in the sound card, the UADC4. The noise floor is now about 9 decibels lower, and the signal level about almost 3 decibels higher. So signal to noise ratio for the average power is improved by maybe 12 dB. So it will be much faster to collect the correlation average. Already after 15 minutes, the sideband noise at 50 Hz is at minus 157 or so, but the imaginary part and the signal is very similar. I have to wait some time. 34 hours, 222,000 averages. I now have a stable spectrum with fairly small fluctuations due to noise, and I can see the separation between the noise from the test object, the real part, which is positive here, and the imaginary part of the correlation spectrum. This separation is very large, so I have good data, and that's so all the way up to 200 Hz. But at very low frequencies there is a problem here. That's 10 Hz is here. Maybe this is still okay at 10 Hz. I will save this and evaluate from paper. And I will also save this amplitude noise. And here is obviously some kind of spur. This cannot be from the device under test, the generator from Wenzel and the filter. I have restarted now with a 6 dB attenuator between the Wenzel oscillator and the filter, and I compensated that by increasing the gain of the sound card by 6 decibels. In total I lost about 4 decibels of the signal to noise ratio, so to get the same accuracy I need a much longer time, but I don't think I need the same accuracy. I just want to have some kind of a look on this. But I have to wait, of course. This is only 1.5 minutes, and the imaginary part and the real part have the same size. After 50 hours, the signal to noise ratio, measured as the separation between the imaginary part here and the noise from the device under test here, is almost 10 dB. Not quite as much as I would like to get accurate readings, but 50 hours is long enough for this. I save these curves, different scales for both amplitude and phase noise, to evaluate from paper. I evaluate the correlation spectra on paper by drawing a straight line where I think the average noise is, and then I measure for the particular frequency, in this case 150 Hz, what is the distance here, and then I know 10 decibels is 43.8 millimeters. So I construct a table like this, and it may be not so accurate at some places where it has been difficult to decide where the noise floor actually is. The signal to noise ratio isn't always so good, and there are spurs on some places. Then I measure the frequency response on this curve that comes from the network analyzer, evaluated the same way. So I have this table, which I will use to compute what is the noise of the filter when subtracting the noise of the Wenzel oscillator. And here are the results. The phase noise from 10 Hz to 200 Hz. Here's the data input that was measured in the previous video. And then the filter from the network analyzer, the filter response. That gives me the ideal sideband noise, phase noise, at the different offsets. And in this column is the values I really measure. And they are not quite as good because the filters has added flicker noise. And then the next column is the difference between the ideal and what I actually see. And that is this column minus that column. And it is computed by first going from decibels to power, and then the powers are subtracted, and then back to decibels again. And these are the results. And as it happens, when I look at the amplitude noise, which is the next group, I find that at 10 Hz up here I have minus 53, and at 10 Hz amplitude noise I have minus 152.7, very similar. And at the other end minus 169.7 at 200 Hz, and 200 Hz for the AM noise, minus 170. That's also very similar. So then I become interested to see what is the difference. Well, here, the difference between the phase noise and the amplitude noise at 10 Hz, 20 Hz, and so forth. And that looks very constant. So then I compute the average, which is the characterization of the total, because the difference between the AM noise and the phase noise is so small, so this can be errors in the measurement. So I say the average is probably more correct than for what the filter is doing. And then the next thing is to look, if I divide that by the frequency, then I find something that is almost constant. It means that this noise goes as 1 over f. So then I take the average of these, and I find minus 145. This is usually called B minus 1. That is the coefficient for the slope by 1 over f for an oscillator, which has that slope. And then I look at the minus 6 decibels data. They are less accurate, the differences are a little bit bigger, but when I compute the average of the B minus 1 computed the same way, I get very nearly the same result. So my conclusion is this flicker noise is independent on the power level, and it is about minus 145 dBc per Hertz at 1 Hertz. I have measured flicker noise in crystal filters before. This graph is from the video nerds60, and a little bit above 1 minute you can find information about the filter I was studying at that time, similar to the present one, but with much lower Q. The present data point, if I take the average of everything, the B minus 1 at minus 144.7, the average of both the measurements at full power and reduced power, and then I draw the straight line at the appropriate slope. Then I arrive here. But this line that I draw now is the phase noise or the AM noise, both at a very similar level. But what I was measuring before, these 2 points, that was the SSB noise, which is the composite noise, which means the sum of AM and phase noise. So it should be 3 decibels above, and that is this blue line, which means I find the same phase noise as I found before, and it's not the same crystals, and it's not the same power, but it is 20 crystals both times. So this seems to be a property of the crystals I'm using. This is a paper. It is from year 2006. The conclusion in the paper is that the flicker noise is dominated by the noise of the crystal. There is a contribution from flicker noise in the amplifier, but it is smaller. 3 different oscillators were studied in the paper, and they all have a B minus 1 in the order of minus 130, or a little bit better. There is a contribution from the amplifier that would have to be subtracted to get the contribution from the crystal. Now I'm using 20 crystals in parallel, and these oscillators use a single crystal. In the paper they also find that this noise is more or less independent of the power level, and it seems to me that the origin of this fluctuations of the resonance frequency is a thermal phenomenon. Atoms are moving crystals from temperature, and this will change the size of the crystal somehow, and it seems to be a property of the material. So having more crystals in parallel means the flicker noise goes down as a square root of the number of crystals, because the noise in the individual crystals is uncorrelated. Well, that is my guess as a conclusion of what I have found in this study and what I can read in this paper. I have now removed these components, so there is no output, and connected the oscilloscope across the crystals here to see what is the voltage when I tune this capacitor for the maximum. And I am doing that with the full power of the Wenzel oscillator. And the level I see is 14.2 volts peak to peak. The power level is 12.8 dBm according to this instrument. With these settings I see 13 dBm. But what I see, which is more important, is that the overtones are very low. This oscilloscope tells me the level is 2.87 volts when I'm running it into a 50 ohm load. And here is another oscilloscope, and it tells me the level is 2.77, also on the 50 ohm input. So here is what I have: 2.82 volts into 50 ohms. That's the average of the two oscilloscopes. That gives me 19.9 milliwatts, 13.0 dBm, in very good agreement with the result from the spectrum analyzer. So input plus 13 dBm, across the crystals 14.2 volts peak to peak. I know the Q is 90,000, you can see that in the beginning of this video. There is no load on the crystals now. The only load they see is from the source here. And the impedance that this thing gives me 50 ohms when it is parallel with 120 ohms. This means that the crystals load the input by 85 ohms and the voltage is 1 volt. So the power in the crystals is in total 11.7 milliwatts, and the power in the 120 ohm resistor is 8.3 milliwatts, in total 20 milliwatts plus 13 dBm. The power in each crystal is then 0.58 milliwatts, and that is a little bit below the maximum rating, which is 1 milliwatt. So almost 3 decibels margin to the highest allowed power. In the next video I will reconnect the filter to the amplifier and make sure I tune it properly, because I want the Q of the filter to be still 90,000. Means I don't want a negative impedance or a load from the transistors. I want they to have an infinitely high impedance. I think that is what I want. And then I will look at the noise added by this source follower, and possibly if there is some contribution from this bootstrap circuitry.